Hello. Welcome to GPU Teaching Kit, Module 9, Parallel Computation Patterns. We are at Lecture 9.3, A Better Reduction Kernel. The objective of this lecture is for students to learn to write a better reduction kernel. Compared to the previous kernel, the new kernel will have improved resource efficiency, improved thread-to-data mapping, and reduced control divergence. Before we discuss the improved kernel, we will first make some observations on the naive reduction kernel we showed in the previous lecture. Recall that the for loop in the previous kernel implements the steps of the iteration. And so in each iteration, we're going to have a if statement that determines whether the thread will be executing the addition or not. So therefore, there are two control paths that will be taken in each iteration: the threads that perform addition and threads that do not. And this is implemented as a control divergence in the GPU. So essentially, the GPU will execute all the threads that take the first path, and then they would come back and execute all the threads that would be taking the second path. Therefore, even though some of the threads appear to not be performing addition, but still these threads will consume execution resources. And in terms of resource efficiency, there's another important observation. Half or fewer of the threads will be executing after the first step. During the first step, all the threads will be performing addition, but as soon as we reach the second step, only half of the threads will be executing, and then the third one, only a quarter of the threads will be executing. So in the second step, all the odd threads are disabled, and after the fifth step, we will have entire warps in each block that will fail the if test, and then so entire warps will be turned off after the fifth step. So this leads us into somewhat poor resource utilization, and but at least when we start to turn off the warps that are completely turned off will not have divergence. And this can go on for a while and up to 6 more steps. And the unfortunate part is during those steps, for the active warps, only one productive thread will be executing, and then and so this will also lead to extremely inefficient resource utilization. One important point of this lecture is that the way that we map thread index into data can significantly affect the resource utilization efficiency. So in some algorithms, we can shift the index usage to improve the divergence behavior. And this is usually because these algorithms use operations that are commutative and associative. And just like reduction, where it doesn't matter how the order in which the elements are accumulated into the final sum. And so in our case, we can actually just slightly change the way that we map index into data so that we can always compact the partial sums into the front locations in the partial sum array in the shared memory. And as a result, we can keep the active threads consecutive, and then as we will show later, this will improve the resource utilization in a GPU. This slide illustrates the design of the new thread to data mapping. And here we still show that in order to process n elements, we're going to use half n slides. So in order to process 8 elements in this example, we use 4 threads. However, these 4 threads are mapped into 4 consecutive shared memory locations. Thread 0 to location 0, thread 1 to location 1, and so on. And we're going to call these use these map locations as their responsible locations. And so during the first step of the reduction, all the threads are going to be adding the elements in their responsible location with an element that is, a thread block away, that is 4 elements away. So three will be added to 4, and 1 will be added with 1, and 7 will be added with 6, and then they will be accumulated into the responsible location for these threads. So in the second step, we only have 4 partial sum elements, and we only need to have 2 threads to add them together. So we're going to only need to have thread 0 and thread 1. And in this case, each thread will be adding an element that is 2 positions away to their responsible location. And then the final step, we only have 2 partial sums. We only need to have 1 thread. So thread 0 is going to add 20 and 5, the 2 remaining partial sums into the final sum of 25. So as we can see that as we reduce the number of threads, all the active threads will be consecutive, and therefore we're going to keep as many of them as possible in a single warp, or the multiple warps in the thread block. So this would allow us to have much less control divergence, and also better utilization, because we will have whenever we use a warp, we tend to use the entire warp rather than only 1 thread in each warp, as we showed in the last few steps of the previous kernel. So now we're ready to look at the code, and we're going the beginning of the code. We're still going to be loading 2 elements for each thread, and then once we finish loading, we're going to still enter into the for loop that implements these steps. The difference is that we're going to use start the stride value at blockdim.x, and this reflects the fact that during the first step, we're going to be adding elements that are blocked dim away from the responsible location into the responsible location for each thread. And then we're going to be reducing the stride size by half as we go to each new iteration. And then by the time the stride reaches 1, we know that 0, that we know that we no longer need to do any more iteration. So we still need to do sync threads, in between the iterations, and then as we enter the for loop, and so that's where we still see that sync threads in the loop body. And then within the loop body, we're going to test whether the thread is less than the stride, and this tests whether the thread should be active. And then we will be adding the partial sum from stride distance away into the responsible location for each thread. If we analyze the execution behavior of the revised kernel, let's say for a 1024 thread block, a thread block with 1024 threads, there will be no divergence in the first steps. We're going to have 1024, 512, 256, down to 32 consecutive threads active in each step. So all we have will be doing in these steps is we're turning off entire warps. And so any remaining warp that are executing will be going full capacity, and all the threads will be active. And then, but once we reach the final 5 steps, there will be only 1 active warp, and we're going to have fewer and fewer threads active in that final warp. So this gives us a much more efficient execution because we're going to have few warps that will have control divergence. Only one warp in the last 5 steps will have control divergence. And also, every time we execute a warp, we tend to execute all the threads. We tend to be doing addition with all the threads in that warp. With this improved kernel, we have completed lecture 9.3 of the GPU teaching kit. Thank you.